Hadoop is a shared nothing framework where each node acts independently throughout the system. A framework where a piece of work is divided among several parallel MapReduce tasks, each task operating independently on cheap commodity servers. This enables businesses to generate value from data that was previously considered too expensive to be stored and processed in a traditional data warehouse or OLTP environment. In the old paradigm, companies would use a traditional enterprise data warehouse system and would buy the biggest data warehouse they could afford and store the data on a single machine. However, with the increasing amounts of data being generated every day, this is no longer affordable nor practical. The world has seen exponential data growth due to social media, mobility, e-commerce, and other factors. 90% of the world's data has been generated in the last 3 years alone, and it is growing at an even more rapid rate. The tools and technologies to accommodate this data growth are referred to as big data. The traditional enterprise data warehouse may not be able to address the big data problem space. The 4 V's of big data helps define the big data problem space and helps us understand how we can use Hadoop to overcome the big data problem. Volume enables handling large volumes of data by adding more machines. Variety provides the ability to process structured, unstructured, or semi-structured files. Velocity adds more machines and provides ability to process data at a faster pace. Variability is the ability to handle inconsistent periodic peaks. Some of the components that comprises the Hadoop ecosystem are Hadoop Distributed File System, MapReduce, Yarn, Hive, Pig, and HBase. Let's take a closer look at each of these components. Hadoop Distributed File System, HDFS, is a system that allows multiple commodity machines to store data from a single source. HDFS consists of a name node and a data node. HDFS operates as a master-slave architecture as opposed to a peer-to-peer architecture. Name node serves as the master component, while the data node serves as the slave component. Name node comprises of only the metadata information of HDFS, that is, the blocks of data that are present on the data node, how many times the data files have been replicated, when does the name node start, how many data nodes constitute a name node, capacity of the name node, and space utilization. The data node comprises of data processing, all the processing data that is stored on the data nodes and deployed on each machine, the actual storage of the files being processed, serving read and write requests for the clients. In the earlier versions of Hadoop, there was only one name node attached to multiple data nodes, which was a single point of failure. Hadoop version 2.x provides multiple name nodes where secondary name nodes can take over in the event of a primary name node failure. Secondary name nodes is responsible for performing periodic checkpoints. In the event of a primary name node failure, you can start the secondary name node using checkpoints that provide high availability within HDFS. Let's take a look at a data warehouse structure example where we have one machine, and with HDFS, we can distribute the data into more than one machine. Let's say we have a 100 gigabyte file that takes 20 minutes to process on a machine with a given number of channels and hard drive. If you add 4 machines of exactly the same configuration on a Hadoop cluster, the processing time reduces to approximately 1/4 of the original processing time, or about 5 minutes. So, what happens if one of these 4 machines fail? HDFS creates a self-healing architecture by replicating the same data across multiple nodes, so it can process the data in a high availability environment. In this example, we have 3 data nodes and 1 name node. The data is transferred from the client environment into HDFS data nodes. The replication factor defines the number of times a data block is replicated in the clustered environment. Let's say we have a file that is split into 2 data blocks across 3 data nodes. If we are processing these files to a 3 data node cluster and we set the replication factor to 3, if one of the nodes fail, the data from the fail node is redistributed among the remaining active nodes. The other nodes will complete the processing function. In Hadoop 2.2, Yarn augments the MapReduce platform and serves as the Hadoop operating system, taking Hadoop beyond simply a single-use data platform for batch processing to a multi-use platform that enables batch, interactive, online, and stream processing. Hadoop 2.2 separates the resource management function from data processing, allowing greater flexibility. This way, MapReduce only performs data processing while resource management is isolated in Yarn. Being the primary resource manager in HDFS, Yarn enables enterprises to store data in a single place and interact with it in multiple ways, with consistent levels of service. In Hadoop 1.0, the name node used Job Tracker, and the data node used Task Tracker to manage resources. In Hadoop 2.x, Yarn splits up into 2 major functionalities of the Job Tracker into the resource management and job scheduling daemons. The client reports to the resource manager, and the resource manager allocates resources to jobs using the resource container, node manager, and app master. The resource container splits memory, CPU, network bandwidth, among other hardware constraints, into a single unit. The node manager receives updates from the resource containers, which communicate with the app masters. The node manager is the framework for containers, resource monitoring, and reporting data to the resource manager and scheduler. HDFS works with MapReduce to divide the data in parallel fashions on local or network machines. The parallel structure requires that the data is immutable and cannot be updated. It begins with the input files, where the data is initially stored, typically residing in HDFS. The input files are split up into input format, which selects the files, defines the input splits, breaks a file into tasks, and provides a place for record reader objects. The input format defines the list of tasks that makes up the map phase. The tasks are then assigned to the nodes in the system based on where the input file chunks are physically resident. The input split describes a unit of work that comprises a single map task in a MapReduce program. The record reader loads the data and converts it into key value pairs that can be read by the mapper. The mapper performs the first phase of the MapReduce program. Given a key and a value, the mappers export key and value pairs and send these values to the reducers. The process of moving map outputs to the reducers is known as shuffling. Partitions are the inputs to the reduce task. The practitioners determine which key and value pairs will be stored and reduced. The set of intermediate keys are automatically stored before they are sent to the reduce function. A reducer instance is created for each reduce task to create an output format. The output format governs the way objects are written, functioning similarly to the input format class described earlier. The output format provided by Hadoop writes to files to HDFS. Hive provides the ability to analyze large amounts of data stored in HDFS. Hive was designed to appeal to a community comfortable with SQL. Hive uses an SQL-like language known as HiveQL. Its philosophy was that we don't need yet another scripting language. Hive supports map and reduce transform scripts in the language of the user's choice, which can be embedded within SQL clauses. It is widely used in Facebooks by analysts comfortable with SQL, as well as by data miners programming in Python. Supporting SQL syntax also means that it is possible to integrate with existing BI tools like MicroStrategy. Hive has an ODBC JDBC driver that facilitates easy queries. It is also beginning to add support for indexes, which allows support for drill-down queries common in such environments. Hive is a framework for performing analytical queries, while its dominant use is to query flat files. There is no reason why it cannot query other stores. Currently, Hive can be used to query data stored in HBase, which is a key value store like those found in the guts of most RDBMSs. And the Hadoop database project has used Hive to query a federated RDBMS tier. Pig stems from the language Pig Latin. Pig Latin is a procedural programming language and fits very naturally in the pipeline paradigm. The main reason is efficiency in computing. When your queries become complex with most of joins and filters, then Pig is strongly recommended. Pig Latin allows pipeline developers to decide where to checkpoint data in the pipeline. That is, storing data in between operations has the advantage of checkpointing data in the pipeline. This ensures the whole pipeline does not have to be rerun in the event of a failure. Pig Latin allows users to store data at any point in the pipeline without disturbing the pipeline execution. The advantage that Pig Latin provides is that pipeline developers decide where appropriate checkpoints are in the pipeline rather than being forced to checkpoint wherever the schematics of SQL imposes it. Pig Latin supports splits in the pipeline. Common features of data pipelines is that they are often graphics, DAGs, and not linear pipelines, since disk reads and writes, both scan time and intermediate results, usually dominate processing of large data sets. Reducing the number of times data must be written to and read from disk is crucial in good performance. Pig Latin allows developers to insert their own code almost anywhere in the data pipeline. This is useful for pipeline development. This is accomplished through user-defined functions, UDFS, and streaming. UDFS allow users to specify how data is loaded, how it is stored, and how it is processed. Streaming allow users to include executables at any point in the data flow. Pipeline also often includes user-defined columns, transformation functions, and user-defined aggregations. Pig Latin supports writing both of these types of functions in Java. These are now being expanded into a number of other scripting languages. Let's take a comparative look at Pig and Hive. Type of flow. Pig is a procedural data flow language. A procedural language is executing step-by-step approach defined by the programmers. You can control the optimization of every step. Hive is a decorative language. The syntax looks like SQL. You can specify what should be done rather than how it should be done. Optimization is difficult in Hive since Hive depends on its own optimizer. Ease of use. Pig requires a learning curve since the syntax is new and different. Hive looks like SQL. Developers seeing Hive recognize the syntax, therefore the learning curve is less. Nature of usage. Pig is recommended for programmers and software developers. The main reason is its efficiency in computing. When your queries become complex with joins and filters, then Pig is strongly recommended. Hive is mostly in analytics areas. Of course, it rules the analytics in Hadoop data warehouse solutions. While generating the reports, people prefer to code in Hive than Pig. If your queries has a minimum number of joins and filters, then you can go ahead with Hive. On the other hand, if the query has lots of joins, Hive may degrade the performance. Type of data. Pig handles both structured and unstructured data efficiently. Hive handles structured data very efficiently. Intermediate layers. Pig represents data in terms of variables. Whenever you want to store an intermediate result, then it's easy to store that in a variable and you can refer to it later. Hive represents data in terms of tables. It is difficult to store the intermediate result in Hive. You have to create a table and insert the values from another table. Thus, when a complex query comes into the picture, Hive code may exceed hundreds of lines. Debugging facility. Pig code can be debugged locally, while debugging Hive code locally is complex and time-consuming. Versatility. Writing user-defined functions, UDF, is easy with Pig. This is more complex in Hive. Maintenance. Pig requires a bit more maintenance than Hive. Hive maintenance is very easy. Persistent. In Pig, you may not retain the values of variables. Every time you have to rerun the Pig code to get the value from a variable. In Hive, the tables, external, will remain with the life. Even if you quit the session, this is because the external tables will still point to HDFS files. Development time. Pig development may require more time than Hive, but it's purely based on the developer's familiarity with the Pig code. Hive, being an SQL-like language, the development time will be less. Compatibility. RDBMS to Pig compatibility is slightly complex since the code syntax of Pig is entirely different. Most of the SQL statements that you executed in your RDBMS can be put directly into Hive. It will work, only a few things need to be modified compared to RDBMS SQL. Handling big data. Pig efficiently handles more amounts of data. Hive sometimes leads to memory overflow or deceptive performance. However, there are several parameters that can be adjusted to address this issue. HBase is a non-relational database that provides random real-time access to data. HBase makes sense compared to HDFS when you need very large tables in order to process billions of rows and columns. Benefits of adding HBase to an implementation includes Java, REST, TRIF, and Avro API access. Let's take a comparison look at Hive and HBase. As mentioned earlier, HiveQL appeals to a community comfortable with SQL. Hive is best suited for ETL and data warehouse, while HBase is best suited when you need random, real-time, read-write access to your big data. Angie Technologies can help with your big data solution. We can help implement Hadoop best practices. Contact our business development team regarding our capabilities.